I'm Noah, and for my AP Pre-Calculus quest, I wanted to explore something that connects math to something I actually enjoy in real life, that being playing the guitar. In this project, I'm going to show how the sound from a guitar string can be modeled using trigonometric functions. So I recorded a short guitar note, analyzed this waveform, and built a trig equation that matches the sound. When I pluck a guitar string, the string vibrates back and forth. These vibrations push the air around them, creating a repeating pattern called the sound wave. Sound waves are periodic, which means they repeat over and over, just like sine and cosine functions. The height of the wave is called the amplitude, which relates to volume. The spacing between the peaks is a period, which relates to pitch. To get real data, I recorded a clean plucked note from the opening of Blackbird by the Beatles. I imported the audio into Audacity so I could see the waveform. This is the full waveform of the guitar note. You can see the sound starts loud and then fades out. But to model the math, I need to zoom in on a small section where the wave is repeating clearly. Here is a zoomed in view of the waveform. Now you can clearly see the repeating pattern, the peaks, troughs, and the center line. This is where I measured the period and amplitude. To find the period, I clicked on the top of one peak, then held shift and clicked on the next peak. Audacity shows a time difference between these 2 points. For this note, the period was approximately 0.0045 seconds. Frequency is the reciprocal of the period. So I calculated f equals 1 over t, so that equals 1 over 0.0045, which equates to about 222 hertz. That means the guitar string vibrates about 222 times per second. To find the amplitude, I looked at how tall the wave is from the center line to a peak. For this note, the amplitude was about 0.13. Now I can build a trig function that matches the sound wave. I started with y equals a sine bx. I plugged in my values. My a is 1.3, and my b is 2 pi f, which is around 2 pi 222, which equates to around 1,396. So my final model was y equals 1.3 sine 1,396x. When I compare the Desmos graph to the real waveform, the shapes match closely. This shows that trigonometric functions can accurately model musical sound. The frequency controls the pitch, and the amplitude controls the volume. It is important to note that real guitar sounds aren't perfect sine waves. They contain harmonics, which are extra frequencies that give the guitar its tone. If I add a second sine wave with twice the frequency, the graph looks even closer to the real sound. This idea comes from the Fourier analysis, which is beyond our class, but it shows how complex sounds can be built from simple trig functions. This project helped me understand how the math we learned in AP Pre-Calculus connects to something I use every day, which is music. Sound waves, frequency, amplitude, and trigonometric functions all work together to describe the vibrations of a guitar string. Modeling a real guitar note with a trig equation showed me that math isn't just in textbook, it's all around us, even in the music we hear. Thanks for watching.